Day 135, Electrostatics example number 42. And this is a good one because it brings back some review topics like free body diagrams, which I will start with here. Well, a couple comments first. These two charges must have the same sign. They're both either positive or both negative because they're repelling each other, kind of like the two balloons in class. But the free body diagrams will be very important here. If I look at the lower left-hand charge and try to draw the free body diagram over here on the lower left, here's that little charge. It has the string tension pulling this way, call that T. It's being repelled to the left by the electrical repulsion from the other charge, let's call that F sub E, and it has gravity pulling straight down. So here's the free body diagram, we'll call that W, force of gravity. That's the free body force diagram for the lower left-hand charge. The lower right-hand charge is just the same symmetrically. I don't really need to draw it, but I will just for practice. It has the tension this way. It has weight, same weight, a lot of symmetry here. And F sub E is the same because those are the two charges that are repelling each other, F sub E. We're looking for F sub E. Now what I'm going to do is I'll concentrate on the free body diagram on the left. I'm going to redraw it way up here in the top right in component form. The only one I got to worry about is T. T has two components. W is already its own component straight down. F sub B is straight to the left, so those are good. What I need to do is redraw that diagram. So that's what I'll do. I'll have W straight down still. It's got F sub E straight to the left. But then you have T sub X to the right and T sub Y straight up. And if I draw that T vector, it looks like this. There's T by itself. And I'm going to draw the components. It's got the XTX, T sub X, X component, and T sub Y, the Y component. I could do this also for the other charge, but I don't need to. It's all going to be the same numbers on both the vector diagrams. So I just need to do this one. Now, because everything is in static equilibrium here, these forces are all balanced. In other words, W equals T sub Y. And I can calculate W, which I will do in a minute here. But first what I'm going to do is I'm going to figure out the angles involved. If I go back to the original diagram, and let me highlight this. I have a triangle, an isosceles triangle here on the original diagram with a 20 centimeter base and 30 centimeter sides. If I drop an altitude straight down the middle, I need to figure out, well, that's a right angle then, altitude. I want to figure out this angle on either side. It's the same on either side. But that angle right there is the same as the angle at which T is pointing the string in my vector diagram over there on the right. And I know that if I look at this blue triangle, this inside here is 10 centimeters, which is half of 20. In other words, if I do sine of theta, that will be 10 over 30. So I go to my calculator, theta comes out to be 19 degrees, which is also the angle in this vector diagram over here, that angle, which is very important, theta. So I know that theta now is 19 degrees. All right, I also know that T sub Y is equal to W, and I know that W equals to mg. W equals mg. I can calculate that. W equals the mass. They tell me the mass is 6 grams, which is 0.006 kilograms times 9.8. So the weight of this little particle, each particle, is 0.059 newtons. That's the weight of each of those. But that's also T sub Y because T sub Y is balancing W. Therefore I know T sub Y equals 0.059 newtons. So if I know T sub Y and I know theta, I can figure out T sub X. Because tangent of theta, I use blue, tangent of theta, and that theta is 19 degrees as we just discovered earlier, tangent of 19 degrees equals T sub X over the 0.059 newtons. So that allows me to get T sub X. I'm going to let you do that. Calculate T sub x. Because T sub x will be equal to F sub E. In other words, once you have T sub x, then you will have F sub E as well. Same answer. Now, where does that get us? Well, now if we go to the original idea here that the two particles are repelling because of the electrostatic force, Coulomb's law, that is F sub E, in other words, is K Q sub 1, Q sub 2, the charge on each of those, which we're looking for here, over R squared. But now, in that equation, which I will circle in red, you're going to plug in here. You know what F sub E is from the right-hand side. Essentially, you'll know that. I'll circle that. You'll know this, and you'll know what R is. It's 20 centimeters, 0.20 meters. So essentially, you'll know this. And then the two Q's you don't know, but they're both the same, so you could make that into Q squared. So you know everything in the blue circles. You plug that in from different calculations we've done, or you will be doing, and then use algebra to solve for Q, because Q1 times Q2 is just Q squared. You don't need the subscripts there, since they are equal charges. And I'll let you finish that problem up.